Good afternoon, students, and welcome to today's class. Today we will be discussing the moment generating function MGF of a Poisson random variable. Moment generating function. Moment generating function. Moment generating function. MGF. MGF of a Poisson random variable. Poisson random variable. Permit me to write R dot V as a random variable. Then let me divide this my board. So first of all, begin by giving the formula for the moment generating function of any random variable x. The formula for the moment generating function of any random variable x is given as m subscript x of t is given as e of tx. So this is the formula for the moment generating function of any random variable x. However, if this x is discrete, this MGF will be expressed this way. So we have e of tx will be given as sum over the range of x of e of t what x p of capital X equals small x. I repeat, the formula for the moment generating function of any random variable x is given as this. However, when we have information that this random variable x is a discrete random variable, this MGF will be expressed this way. The use of sum here is because this MGF is discrete in nature. Else, we could have gone for integral if it were a continuous random variable. Okay? Now, therefore, this is the formula for the MGF of any random variable x. This is the formula for any random variable what? X that is discrete in nature. Where P of capital X given equals X is what we call the PMF, probability mass function of this random variable what? X. And we are discussing the Poisson random variable. Therefore, we are going to give the PMF of a Poisson random variable. We now say but. We say but for a Poisson random variable, for a Poisson random variable, P of capital X equals small x is given as lambda raised to power x exponential minus lambda all over what? X factorial, where x takes a range from 0, 1, 2, down to positive infinity. So for us to be specifically talking about the MGF of a Poisson random variable, we are going to remove this P of capital X equals small x and replace with the PMF of a Poisson random variable. So I will say therefore, that my E of tx is given as, here is my sum, I will write sum over the range of x. Here is my E of t what? X. I will write this again, I will write this one, which of course is the PMF of a Poisson random variable. So I have lambda raised to power what? X, exponential minus what? Lambda, all over x what? Factorial. Now, if you look at this equation, you find out that this exponential minus lambda does not contain the variable what? X, and therefore can be brought outside the word the summation sign. So what we now have becomes exponential minus what? Lambda. We have sum over the range of x. Then we have what? E of t what? X lambda raised to power what? X, all over x factorial. Okay? Now, of course, here is x and here is x. So I can easily express this in this way that it becomes that this is the same thing as, here is my exponential minus lambda for this. I have sum over the range of x. Here becomes my what? E of t, and then lambda all raised to power what? X, all over x what? Factorial. This is raised to power x. Of course, if you want to return back here now, here is lambda raised to power x, which is what I have here. Here is my exponential t multiplied by this x, which returns to this. So we move ahead. We now say, therefore, this equals, here is my exponential minus lambda. Exponential minus lambda, I'll open a bracket. Of course, we are discussing Poisson random variable, so the range begins from 0. This x begins from 0 down to positive infinity. So when x becomes what? 0 here. 0 raised to power anything is what? 1. 0 factorial is 1. 1 divided by 1 is what? Is 1. I will say plus. I will say 1 plus. Then when x becomes what? 1, we have exponential t of lambda raised to power 1. We'll return something like lambda exponential t. Okay? Or e raised to power what? T. All over what? 1 factorial. And 1 factorial still remains what? 1. So which means what I have here is the same thing as what? Lambda exponential what? T. Then I will now say plus. When my x becomes 2, it's going to be lambda exponential t raised to power 2. It becomes lambda exponential what? T, all raised to power 2, all over 2 factorial plus. Then it continues down to infinity. And we are told that according to the Maclaurin series, that whenever we have 1 plus lambda exponential t plus lambda exponential t raised to power 2 all over 2 factorial plus down to infinity, that it is the same thing as, that is what is in bracket is the same thing as, we have exponential, what you have here, lambda e of what? Of t. If what I have in this bracket, according to the Maclaurin series, is given as this, and do remember that I have exponential minus lambda at, before, so I will say therefore that my e of tx, which of course is what we are solving, the MGF of a Poisson distribution, becomes exponential minus lambda multiplied by exponential lambda exponential what? T. Now I have lambda here, I have lambda here. So I can easily factor. And then this thing becomes what? Exponential what? Lambda, you open a bracket. What we have here is what? E of what? Of t minus. What will be remaining here should be what? 1. You close it. So, and this thing is what we call the MGF, moment generating function of a Poisson random variable x. So anywhere you see this, refer to it as the MGF of a Poisson random variable x. And of course, we know that there is a very important characteristics of the MGF. That characteristics is that when the MGF is differentiated once, we get the mean of that random variable. That is to say, that when I differentiate this MGF once with respect to what? To t, the answer I'm going to get is going to be the same thing as the mean of the Poisson random variable. And in one of our previous classes already we had proven that the mean of a Poisson random variable x is lambda. So we want to know whether if we differentiate this thing once and evaluate it when t is equal to 0, that we'll be able to get what? Lambda. First of all, these are MGF, which we began from here. I do remember I said that this formula here is the formula for the moment generating function of any random variable x. It is expressed like this. But when we have additional information that this random variable x is discrete in nature, This MGF now will now be expressed as this, where I am making use of what? Of sum, and I'm making use of what? PMF of that random variable, what? X. However, we are discussing a Poisson random variable, what? X. And the PMF of a Poisson random variable X is given as this. Okay? Therefore, for me to solve the MGF of a Poisson random variable, I am going to replace the PMF written here with the PMF of a Poisson random variable X. That's what I have here. Instead of writing this PMF here, I am replacing with that of what? Of a Poisson random variable. So that's what we have here. And then remembering that this exponential minus lambda is a constant here, I brought it outside the what? The summation sign. Then what I have here is what? Exponential tx, and what I have here is what? Lambda raised to power what? X. So trying to bring out what is common, then I said, okay, fine. This one contains x, this one contains x. So this thing can be expressed this way. Exponential t lambda all raised to power what? X. All over what? X what? Factorial. So what I have here, exponential minus lambda, exponential minus lambda, I open a bracket. Remember, we are discussing Poisson random variable that its range begins from 0 and ends at infinity. So that was why I said, okay, fine. When x becomes what? 0, what I'm going to have here is what? The whole of this inside here raised to power what? 0, all over 0 factorial, which is 1. When x becomes 1, the whole of this thing raised to power what? 1, all over 1 factorial, which is the whole of that thing. Then when x becomes 2, then that whole of that thing will be raised to power 2 all over 2 factorial down to positive infinity. And I'm saying that according to the Maclaurin series, that the whole of this thing inside the bracket, which is 1 plus lambda exponential t plus lambda exponential t raised to power 2 all over 2 factorial plus down the line up to infinity, is expressed as lambda exponential t. In that case, what I'm going to have is this exponential minus lambda, which what I have here, multiplied by exponential lambda exponential t, which is what I have here. Now I have exponential lambda here, I have exponential lambda here. So I can factor out exponential lambda. If I factor out exponential lambda, what I'm going to have now remaining here will be exponential t inside the bracket, which is what I have here. Minus what? 1, which is what will be remaining here. So this is the MGF of a Poisson random variable. It is very clear. So we are saying that when we differentiate this MGF with respect to t and evaluate it when t is equal to 0, that we are going to get the mean of a random of Poisson random variable. Let us try it out. Permit me to clean here. Okay? So let us differentiate what one once. Okay? So we are saying that we want to differentiate this m of x of t once. Differentiating it what once. And earlier we have gotten that this is our MGF of a Poisson distribution. So I am also going to differentiate this in once. So this is the same thing as d. Okay, and of course, when we differentiate it now, we evaluate it now when t is equals to what? 0. So this is the same thing as I'm going to differentiate this quantity, so which is e of lambda minus 1, then the what? dt evaluated when t is equals to what? 0. Now I want to make this thing clear so that we can see it clear. I can decide to say let y equals exponential lambda exponential t minus 1. Then let u equally be lambda exponential t minus 1. So I will say therefore my y is equals. Remember that y is equals to the whole of this. But u is everything that is here. So my y is exponential what? U. So therefore, differentiating this thing is at the same thing as differentiating y with respect to what? To t. So I will now say therefore my dy dt is given as, I will now differentiate this y with respect to u, which is dy du. multiply by. I will now differentiate this u with respect to t, which is du, the what? The t. This is equals. dy du, when we differentiate exponential u, it is the same thing as exponential u. So what I have there is what? Exponential what? U. The sign here is multiply by. Multiply by. I want to differentiate this u with respect to what? To t. And differentiating this u with respect to t is lambda et. Because you can decide to open this thing this way. Lambda times et is lambda exponential t minus. Lambda times minus 1 is what? Lambda. Or lambda times 1 is what? Is lambda. So if I differentiating u with respect to t, this quantity doesn't contain t and as well becomes what? 0. So what you have here is what? Lambda et. Because differential value of exponential t is exponential t. So what we have there is what? Lambda et. And of course, you know that this u I have here is the whole of this. So you now say therefore that my dy dt is given as this exponential. This my u becomes the whole of this I have here. Lambda exponential what? T minus 1 multiplied by lambda et. I want to evaluate this at t equals to 0. So at t equals to 0. Permit me to complete the proof here. Or let me even come here still. When t becomes 0, 0 goes in here. So what I have here becomes exponential 0, and anything raised to power 0 is 1. And what I have here is 1. 1 minus 1 is 0. 0 multiplied by lambda is 0. Exponential raised to power 0 is 1. So this equals to 1 multiplied by. Here, what I have is what? Is lambda exponential. T is going to become 0. Exponential 0. And anything raised to power 0 is 1. So what I have here is what? 1 times lambda times 1, which is equals to lambda. And yesterday during our class, we showed that the mean or the expected value of a Poisson random variable is lambda. And they are saying here that when we differentiate the MGF of a Poisson random variable once and evaluate it when t is equals to 0, that we are going to get the expected value of a Poisson random variable. And this is what, of course, we have shown here. This is equals to lambda. So what we did here was differentiating the MGF once, evaluating it when t is equals to 0. It's the same thing as differentiating this quantity now, which of course is the MGF of a Poisson random variable. Once, let me put this prime here, once and evaluating it when t is equals to what? 0. Trying to make this differentiation clearer to our students, I decided to say, let y be that quantity which we are differentiating. And let the whole of this power I have here be what? Be u. Such that my y becomes what? Y is equals to what? Exponential u. So differentiating this is as well as differentiating what? Y. So dy dt will now be dy du multiplied by du dt, which is of course what we had here. And then trying to evaluate it now when t is equals to 0, we arrived at this. Okay? So that is how to arrive at the expected value of a Poisson random variable from its MGF. We can equally arrive at the variance from the MGF by differentiating this MGF what? Twice. And to differentiate this MGF twice, what we are going to do is this. So permit me to clean here. There's nothing difficult here. Okay? You remember that when we differentiated once, this was the answer we got. So if I want to differentiate this thing twice, it is going to be differentiating this thing twice, then with respect to what? To t of that quantity, which is the exponential lambda exponential t minus 1. But of course, we already have differentiated once before and we arrive at this answer. So differentiating twice is the same thing as differentiating once of the answer we got when we differentiated once earlier, which is what? Lambda et, which is what I have here, exponential lambda exponential what t minus 1. This is what we now have. Permit me to remove what came up on my screen. So this is now what I have. And when I have this, of course, I'm going to use a product rule. You understand? To differentiate this. And it is going to be, I'm now going to say here that my dy du, dy dt is equals u dv dt plus. I have what? V du dt. I am calling this quantity u and I'm calling this quantity what? V. So for me to write u, I am going to write lambda et. So I have that this is equals to what? Lambda et. I want to differentiate v. Differentiating v means differentiating this. And we have shown earlier that when we differentiate this quantity, what we are going to get is a lambda exponential what? What we are going to get is what? Lambda exponential t. Then we have exponential lambda e of what? Of t minus 1. We have shown this in earlier. This was what we got earlier, which is of course what we are trying to differentiate here. Then I will now say plus. I will write down v the way it is, which is this quantity. So is that exponential what? Lambda exponential what? T minus 1 multiplied by, I will differentiate u, and this is u. Differentiating u is the same thing as that quantity, which is lambda exponential what? T. So I want to evaluate this thing when t is equals to 0. Evaluating this when t equals to 0. 0 goes in here. What I have here is now lambda. Because when 0 comes here, exponential 0 is nt raised to power 0 is 1, multiplied by lambda is lambda. The same thing here, so what I have here is what? Lambda, multiplied by. When t becomes 0 here, I have e raised to power 0, which is 1. 1 minus 1 is 0, multiplied by this lambda is 0. E raised to power 0 is what? Is 1. The sign here is what? Is plus. When I evaluate the whole of this, it is still what? 1 multiplied by. When I come here, it becomes what? Lambda. So that what I have here becomes what? Lambda raised to power 2 plus what? Lambda. And of course, we have to remember that the variance of a random variable x is given as var of x is given as e of x raised to power 2 minus e of x all raised to power 2. E of x raised to power 2 is referring to this second derivative, which of course gave us this quantity. So this now is equals lambda raised to power 2 plus lambda in place of this minus. In our previous class already we had shown the expected value of a Poisson random variable is lambda, which of course is what we equally showed today when we differentiated the MGF what once. So meaning that what is inside this bracket is lambda. So I have lambda all raised to power what? 2, which becomes what? Lambda raised to power 2 plus lambda minus lambda raised to power 2. This will cancel this, and then this equals what? Lambda. Therefore, my e of x is equals to lambda, and my var of x is equals to lambda. So we can actually arrive at the moments of a Poisson random variable from its MGF by differentiating the MGF once to arrive at the mean or expected value, and differentiating twice and applying the formula of a variance to arrive at the variance of a Poisson random variable. We already had classes on the Poisson random variable regarding introduction and solving problems there. We refer you to that class for an in-depth knowledge or understanding of a Poisson random variable. We have actually had a class on the proof of the expected value and then the variance of a Poisson random variable. We equally refer you to that class now for an in-depth understanding of a Poisson random variable. After now, we are going to go into what we call the characteristics function of a Poisson random variable. Before we now go into Poisson approximation to binomial distribution. Thank you very much, and stay put. Do not forget to subscribe to our YouTube channels, as we are committed to making sure that we render some of these things that look abstract to you in a very understanding manner. Thank you very much.